All right, so I'm just gonna write here, recalling. Just those two equations that x of t, this is from one of the previous pages, c bar 1 a constant, exponential minus lambda 1 t plus c bar 2 exponential of minus lambda 2t. Okay, or after some deviations, we concluded that you can write this as this equation over here. All right, I'm just going to rewrite. So this one over here. And then we do the three different cases. You can write or x of t equal to c bar 1 exponential of minus c plus c squared minus 1 square root omega n t plus c bar 2 exponential of minus c minus c squared minus 1 square root omega n t. Okay, we need to look at three different cases. Case 1, critically damped. Case 2, underdamped. Case 3, overdamped. All right, so case 1 is critically damped. Which basically means the damping ratio is equal to 1. Okay, so in that case, what is happening? When c equal to 1, you see the term within the square root goes to 0, all right? But if you compare then this one to this one, it's like saying that there's only one lambda, and that one is equal to lambda 1, which is equal to lambda 2, no? Over here, we just left with this term will be 0, this term will be 0, we have twice the same one, no? Which would be the same thing as in lambda 1 equal to this lambda 2 over here. Okay, so this will be the case. Let's say we have repeated roots of the characteristic equation. Okay, so in that case, I'm just going to write the top equation. You have x of t so this means like enter. Okay, so I'm going to substitute into the above equation. You get c bar 1 exponential, and x is equal to what? To minus omega nt plus c bar 2 exponential of minus omega nt okay. So be careful here, because when there is repeated roots, what happened? Can you do this? When you have repeated roots, if you remember from differential equations, what you need to do is add to the second solution the variable t. Okay, that's because of repeated roots. That's the solution. Or you could just rewrite the solution as x of t equal to exponential of minus omega nt bar of c bar 1 plus c2t. Okay, so this is the general form for the critically damped. But last time we said that this time we're going to solve the whole problem using So we need to find the two variables. We say for all cases, we follow this. We're going to use these following initial conditions: that the initial deformation at t equals 0 is equal to x sub naught, and the initial velocity at t equals 0 would be x sub naught or just v naught. All right. So we say here applying initial conditions to determine the constant c bar 1 and c bar 2. Okay, so the first boundary condition we had is x at t equals 0. Let's say you move everything, you displace the whole system a certain distance, x sub naught. Okay, so in that case, if we substitute into this equation, what are we going to have? This will give you what? So we'll have, so this will be equal to 1 now. Then this will be C1, and this will be 0. But this is equal to x sub naught. So this will mean that C bar 1 should be equal to x sub naught. Yeah, by just substituting directly into that equation. So we know the first part, the first constant of integration is x sub naught. Now, our second condition is to know the velocity. So we know x dot of t at t equals 0 will be equal to x dot 0. We can just call it v naught, but let's just say x dot 0. So in this case, we need to be a little bit more careful, because what do we know? We know x of t. So let me write it here. X of t is exponential of minus omega and t c1 plus c2t. Okay, so x dot of t will be equal to what? Will be equal to minus, so let's expand, this will be equal to, if you want, c bar 1, and we put the minus omega n exponential of minus omega and t. I hope you see what I'm doing. Multiply these two together, and then you take the derivative, will be c1 minus omega n times this one, no? Yep. Okay, we do the same thing for this one, but for this one we need to be careful, because if there's two variables, you need to take the derivative by parts, no? The variable of uv is u prime v plus uv prime. Okay, so let's do that one here. So the first one will be, minus c bar 2. So let's just do the same thing here. Omega n exponential of minus omega n t times t. And now plus c bar 2 exponential of minus omega n t. So this one would be the derivative of c2t exponential of minus omega n t. If we do the first part, will be c2t times minus omega n exponential of minus omega n t. And then the second part would just be the derivative of t is 1, so it should just be c2 exponential of minus omega n t. All right? Okay, so let me try to organize this a little bit better. So at x bar of t at t equals 0, what will you have? So when it is equal to 0, this will be equal to minus c1 omega n. This will be equal to 0, no? Because t will be equal to 0. This term will be equal to 0. And then at the end, so it will be, if you want, minus 0 plus c bar 2. And we know this needs to be equal to the x dot sub 0. But at the same time, we already solved for c bar 1. Oops, forgot to put the bar here. C bar 1 is actually equal to what? To x naught. So from here, we can get that minus x naught omega sub n plus c bar 2 equal to x dot sub naught. Or from here, we can just say that c bar 2 will be equal to x dot naught plus omega n x sub naught. All right, if you want, let me just call this equation here, I don't know, I or 1 in Latin. And now the only thing we need to do is substitute C1 and C2 into the solution, okay? And we get the expression. So substituting C bar 1 and C bar 2 into, let me just rewrite it. I think it would just be easier, be a bit more clear. X of t exponential of minus omega n t C bar 1 plus C bar 2. We're going to get x of t to be equal to, let me just change the order, will be equal to x sub naught plus x dot sub naught plus omega n x sub naught exponential of minus omega n t. Okay, so this will be the critically damped solution. Okay, and at the end, we will plot all these solutions. But basically, over here, what you see, this basically will be a constant, no? All right. So this should take the shape when it's gonna, if you plot it, of this function here. So this is the exponential function with the minus sign. So you know the exponential function, if it's positive, it's gonna grow very quick. All right. But if it's negative, it means it's going to decrease very quick, no? Yeah. So at the end, the limit, if you want, of this solution should be 0 after a certain time. We can plot it, but we'll plot it later. Okay, guys, so somebody mentioned to me that I forgot the t over here. It's true, I put the C2, but I forgot to put the t, so put over here t. Well, and if you want, let's just write what we just comment, that the limit of x of t as t goes to infinity is basically, this is a constant, so this is basically the limit of exponential of minus omega n t as t goes to infinity, and you know that this basically will go to 0, no? Okay, I mean, you know that when it's damped, at the end, ultimately needs to be 0. Okay? All right. So, case 2. So, our case 2 is underdamped. That means that the damping ratio is lower than 1. Okay, and this is obviously the most common case and the one of more interest, okay? So solution probably is going to be a little bit longer. All right, so in that case, if this is lower than 1, what does that mean for our solution over here? Is that the square root is going to become a complex number, no? Because it's going to be negative. So in that case, that means that this ratio here will be equal to 0. So basically, we'll have complex numbers, and we know that square root of minus 1 should be equal to I, okay? By definition, the complex numbers. All right, so that means that the two roots that we have, remember this root is equal to this one is equal to this, so these values within the square root becomes complex numbers, okay? Imaginary numbers. So this means, this implies that the first root, lambda 1 will be equal to C plus I 1 minus square omega sub n, and lambda 2 will be the same thing, minus I omega sub n. All right, so now we go and substitute into the general solution. The general solution x of t, which we say is of the form x of t c bar 1 exponential minus lambda 1t plus c bar 2 exponential minus lambda 2t. All right, so equal to c1 exponential of minus xc plus I square root of 1 minus xc squared omega n t plus c bar 2 exponential of minus xc minus I 1 minus xc squared omega n t. Or we can simplify this as x of t equal to exponential of minus c omega n t. of c bar 1 exponential of minus I xc of 1 minus x squared omega nt plus c bar 2 exponential of positive I 1 minus x squared omega nt. Okay, so as before, this is a general form of the equation, and now we need to determine the variables C1 and C2. So instead of dealing with this exponential notation, we're going to use the Euler identities to transform these exponentials into cosines and sines. All right, don't worry about all these derivations and all that equations. At the end, I will provide you with the class notes with a summary of equations that I have over here. You see summary of results that combine all those derivations that we're doing now. All right. So, but I think it's important that you see the process, because when you solve the problems, basically you do exactly the same thing. You need to go through the same steps. All right. Okay. So using Euler's identities, which are what? The Euler's identities are the relation that says that exponential to I to the theta is equal to cos theta plus I sine theta, and that the exponential to the minus I theta is equal to cos theta minus I sine theta. All right, so using these two relations, let's rewrite this equation out here. Okay, so this will give us that so using the Euler identities, we can rewrite x of t as what? So the first one remains unchanged, minus xc omega nt. And now what's going to happen with C1, C2? So we're going to have cos theta, this part is the same. All right, the first part. So maybe we can combine it right away. We'll have what? C bar 1 plus C bar 2. No, we combine the first part. And this will become what? Cosine of square root of 1 minus c squared omega nt. And now the second part will be what? So use the I part. So you see the first one is positive. So one will be negative. So it will be what? So which one of the C's should be negative? The one that has the negative sign up front is the C1, no? So basically this will be gonna I C bar 2 minus C bar 1 should be a negative 1. And then we need to use the sine part. So this will be sine of 1 minus c squared omega nt. All right, or Or we have x of t, to simplify the bit notation, will be equal to exponential of minus xc omega and t. And we have here a bar cosine of the square root of 1 minus c squared omega and t. Oops, sorry. No, that's fine. Plus b bar sine 1 minus square root omega and t. So I know it's not very clear here. Can you read that, or do I need to rewrite it? So this term over here is the same as this one, time omega and t. Okay, where obviously the a bar is the c bar 1 plus c bar 2, and the b bar will be the I c bar 2 minus c bar 1. All right, guys, so now I'm not going to redo the derivation. Last class, or maybe before that. Yeah, before that, where is it? Yeah, here it is. Remember, we said that this type of equations, a cosine omega nt plus b sine omega nt, so this is page 26, can be rewritten under this form. Yeah, and I did the proof, no? Okay, so I'm not going to redo the proof. Just remember that we can rewrite this as the form of the amplitude, sine, or actually it could be sine or cosine, because what do we say? That the sine is the same thing, that the cosine is the same thing as the sine, but you just move a certain angle, no? A phase, okay? Or if you want the cosine is, or the sine is the same as the cosine, you move at a certain phase. So this equation, actually you could write it as amp sine or cosine, but what's important is that you can write under this form. And you see this one, this part over here is the same thing, no? It's a cosine plus b sine. So all this part, we can write it as just one term. All right, so following the same procedure as in pages, I think it was page 26, 27. X of t can be written as x of t equal to the amplitude exponential of minus c omega and t times sine one minus c squared omega and t minus phi. Where at as before, the amplitude would just be equal to the square root of A bar squared plus B bar squared, and you take the square roots. And the phase angle will be equal to the negative of the inverse tangent of A bar over B bar. Okay, all this is on page 26, 27, okay? We did the derivation. Okay, but now let's not lose track because I know we changed rotation. A bar B and B bar B are still in function of C1 and C2, no? Okay, so now this is a general form of the solution, but for the two specific initial conditions, we need to determine C1 and C2, okay? Same procedure as before. So 36, 37, 38, 39. Okay, so next, the two constants, C bar 1 and C bar 2, are determined from the initial conditions, which are what? X of t at t equals 0 equal to x sub naught, and x dot t at t equals 0 equal to x, the velocity 0. Okay, so I will provide this page over here for you, all right, on the class notes. Let me zoom in, but I mean, I don't want to rewrite all this stuff, okay? So to tell the truth, when I did it using, this is a Maple. You want, I can write it here, Maple file, which is good because Maple, so what I did here is just rewrite the equation, C1 exponential of plus C2. So I just rewrote the equation under this form over here, okay? And now I can take what? I can apply the first boundary condition, and I can apply the second boundary condition. So if you see, I took x of t, so this is x of t, gives you this expression. This is the one we have. And now find here the velocity, okay? dx dot. So it gives you all this integral over here. Now, if I go and apply at t equals 0, so this is equation 1. Equation 1 will be equal to what? X, when you substitute here, t by 0, we are left with what? This should give you 0 because you have, let's see, you multiply everything by 0, so you have 0 plus 0, no? Okay, so you have 0, and the second equation is just going to give you C1 plus C2. So now you have two equations for two unknowns. Basically is what I say here, two equations. Equation 1 should be equal to what? X sub naught, correct? And equation 2 should be equal to what? X dot sub naught, which is V sub naught. But solve for C1 and C2, and this is what it gives me. C1, this long expression here, C2, this long expression. But what is nice about Maple is that then I say, okay, we know that A is equal to C1 plus C2. If you go and simplify that expression, it gives you that A bar is equal to X sub naught, and B bar is I of this expression here. Okay? So I give you this on the notes. All right, so you have it. So this is really A bar. This is really B bar. Okay. If you want, this will be A bar, this will be B bar. But I don't feel like writing all this. So I'm just going to give a summary here, and I will attach this page. So C Maple file, and from Maple file we got that A bar, which is equal to what? C1 plus C2, C bar 1 plus C bar 2 will be equal to X sub naught, and that B bar, which is equal to I C bar 2 minus C bar 1 is equal to X dot sub naught plus C omega n X sub naught divided by square root of 1 minus C squared times omega sub n, and all these terms should be a complex number I. Okay, I'm just copying this one. This capital I here is the letter I. All right, so let me not forget to provide this page. I will put it right after the 39. Okay, so last step, substituting A bar B and B bar into X of T. So X of T should be this expression over here. Okay. We're gonna get what? X of T. So let me write it. So X of T equal to exponential minus C omega n T A bar cosine 1 minus C squared square root omega n T plus B bar sine 1 minus C squared omega n T Okay, so now you know the value of A and B, all right? So I don't know if I need to, do I need to substitute the value here for A and B into this equation? Let's just do it. It'll be silly, but what can we do? Exponential of minus C omega n T. Exponential, so this will be X sub naught cosine 1 minus C squared omega n T plus, I'm going to put to the line because it's a long term, B is equal to X dot sub naught plus C omega n x sub naught 1 minus c squared omega n I sine 1 minus c squared omega nt. Okay, this is very complicated, but remember that you can always rewrite this as what? Under this form, no? Where you know that the amplitude will just be this square over here or this one square. All right, when you substitute for A and B. Okay, so let me just write this one. Or it is easier to use x of t equal to the amplitude of exponential of minus omega and t times sine 1 minus c squared square root omega and t minus phi. All right, so let me just square all this stuff here. Okay, so this will be what? The solution for underdamped. Okay, so let's see. So solution for underdamped. All right, so let me organize a bit the class notes here before we move to the next one. The last case we have, I want to put this page here. 38, 37, 36. Okay. All right, page 40. Okay, we can plot the solution. So plot for underdamped case. So this is x of t in function of time. Okay, so generally what people say the way to plot it is to realize that it's going to be compressed between two exponential functions, but it's going to be damped pretty slowly, okay? So let's see, can we do this? Okay, and it keeps going down, down, and down. Well, this will be from the figures, this will be the phase angle. But now, what do you see? The amplitude is not constant because of the damping. If you remember, going from one point to the other is like going all around the circle once. So this is the period. So the period tau sub naught is equal to 2 pi, and generally is equal divided by omega n when it's no damping. But when it's damping, it's divided by omega d. All right. And I give you now omega d is the damp frequency, and basically it's equal to 1 minus the damping ratio, omega sub n. And here the amplitude, you see the amplitude will decrease in function of time at the rate of minus omega nt. Okay, so let's see, we have time to do case 3. Case 3 is the overdamp. So when the damping ratio is higher than 1, so in that case, what's going to happen to this term? The one under the square root is going to be positive, no? So we're going to have two, instead of having two complex roots, we're going to have two real roots. And basically the rest will be the same procedure. So we have that since the damping ratio is positive, that means that this will be positive. And that means that we're going to have two real roots. Okay, and the value of those two real roots, lambda 1 equal to xc plus c minus 1 square root omega n, and the lambda 2 is the same thing but with a minus sign here. Okay, I hope that by now I don't need to write everything, but now what do? We substitute. So substitute lambda 1 and lambda 2 into general solution. X of t, the one I wrote here at the beginning, let's just rewrite it. C1 exponential of minus lambda 1t plus C2 exponential of minus lambda 2t. So C bar 1 exponential of minus lambda 1t plus C bar 2 exponential of minus lambda 2 bar t. And this is going to give us the general form of the solution to be equal to what? C bar 1 exponential of this term over here. So it will be minus xc plus c squared minus 1 okay, omega and t plus c bar 2 exponential minus same thing but with a negative sign omega and t. Okay, so now what do we need to do? Find C bar 1 and C bar 2 using the initial conditions. It's over again, over and over the same procedure, okay? So let's say applying initial conditions to determine C bar 1 and C bar 2. Okay, so what is the first initial condition? X of t at t equals 0 is equal to x m naught. So maybe this one, since it's easier and they don't use maple, but we could go and use maple, it would be just faster there too. All right, so I have the function over here. So what do we have? This will be 1, no? Exponential of 0 is 1. Exponential of 0 will be 1. So we'll have first equation will be C bar 1 plus C bar 2 equal to x sub naught. We say this will be our equation 1. And our second initial condition is x dot of t at t equals 0 is equal to x dot 0. Okay, so all right. So what is that going to give us? If we have this equation here, we have it on top, we have that d x of t dt will be equal to what? It will be equal to C1, C bar 1, times all this term over here. So it will be minus, actually should be minus C bar 1 xc plus x squared minus 1 omega n. Can I do one thing to be a bit faster for the notation? Remember, this is at t equals 0, no? So the exponential of all this term over here, exponential of 0 is 1, no? Okay, so if I evaluate now that term, I don't have to write it over here. So this should just be minus C bar 1 xc plus xc minus omega n plus the 1 here. And the second one will be basically the same thing, minus c bar 2 bar, but this time will be xc, and instead of a positive value, we'll have minus 1 omega n. And this should be equal to x dot sub 0. So basically this will be, okay, let me just write it for clarity, but I'm not going to change anything. So it will be equal to, could put everything positive to the truth. C bar 1 is a negative value minus C bar 2 and equal to x dot 0. So this will be our equation 2. Maybe I should have written this one in blue, but too late. Too late. Okay, so solving equations one and 2 for C bar 1 and C bar 2. I probably did that in Maple, even though it's not really that complicated, because you can just rewrite C1 will be x dot minus C2. Yeah, so type in error here. So guys, yeah, the omega n multiplies everything. So it's the parenthesis is here. And here's the same thing. And the same thing over here. And the same thing right here. Yeah, sorry, good call. Sorry, see, it wasn't paying attention. So if you solve these two equations, we get that C bar 1 is equal to negative x sub naught omega n C minus C squared minus 1 square root plus x sub naught divided by 2 omega n x squared minus 1 square root, and C bar 2 is positive x sub naught omega sub n parentheses of C plus C squared minus 1 square root. Be careful, here's sub naught plus x sub naught divided by 2m x squared minus 1 square root. So as you can imagine, I'm not going to rewrite the same equation part in this term. I'm just going to say the general solution for the overdamped case is obtained by substituting C bar 1 and C bar 2 into the equation x of t equal C bar 1 exponential of lambda 1, which is equal to minus C plus C squared minus 1. I have to be careful here with the omega t to make sure it's outside, plus C bar 2 exponential of minus C minus C squared minus 1 omega nt. And this is the overdamped solution. Yeah, so this is not m, is omega sub n, okay? All right, guys, so basically this is the case, it's overdamped. So what's gonna happen? The solution should we go very quick to 0, no? We can imagine, all right? So I leave you this over here. And I thought I had those figures. Oh, okay, here they are. That's what I was looking for. Okay, so guys, what I'm gonna give you, I'm gonna put that at the end of the notes. Like a summary of what we just did. So critically damped, it will give you the solution, okay? For C1, that was, remember, that was C1, that was C2 now, the expression. For the underdamped, this you could use the C of these terms over here, but basically same expression of the solution. All right, so the exponential decay, this is a periodic motion. An alternate form to rewrite it is under this form, as we did. This will be the amplitude. The overdamped case, the one we just did, here the person substituted those values. I wasn't willing to do that, no? Okay, but I give you a summary. So here, not as important, but here you give you a plot basically of what will look the solution if you plot them. So obviously, if you have the what's generally hard to define is what is the critically damped and the overdamped. All right. So the critically damped is the one that goes the fastest to 0, like the black solid line, and the overdamped is the dashed line. All right. But you see that both of them go pretty quick to 0, no? Okay. And that the underdamped case is the one that, depending on the parameters, it can stay there forever. And this black solid line over here will be the undamped case, meaning that the amplitude will remain the same all the time. Okay. All right. So summary of result. This, let's organize the notes. So when I scan them, everything is clear. So 41. I have here 36, 37, 38. The maple file 39, 40. And I'm going to add these 2 pages. And I also kind of plot it on my side using MATLAB. Basically, this will be the critically damped for one case of data to show it. For the same data for the underdamped, you get the type of response. Okay, but look at the scale of time here between 0 and 2 seconds. That's it. It's done. No, the solution is 0. Here I go up to 50 or even at 35, 40. There's still some amplitude. All right, and for the overdamped, probably for the same value of K and M, you see the response even within 1 second is already pretty close to 0. All right. But if you remember, we said that doing this is like going around the circle. So I like more this type of representation. To me, they mean more. So if the case was, if it was no damping, this should look like what? Like some type of ellipse, no? Solid ellipse. If you have underdamped, what's going to happen? That ellipse is slowly going to decrease in radius, no? Until it goes to 0. If you have now the critically damped, this is the one that should go the fastest to 0. You see, you go from this x sub naught, you will go straight to 0, okay? Through the blue dotted line. And then for the overdamp, it is the orange one. You will still go to 0, but it will take a little bit more time. All right, so I will add also these two figures to the class notes. All right, and that will be it for today.